Okay, so this was your homework. I asked a couple people already. I said that they had already about 6 people already turned it in. I was like, hey, how long did it take you to do it? And well, I was done before the end of class. All right, so today is the second true geometry lesson. So if you haven't already done it, make sure the homework makes its way to the box. You want to pass it left, or just make sure it's in the box before the end of the day. I will not be here tomorrow. So I'll be here at the start of class, but around 2 o'clock, I just want to leave. We're going to do a review for tomorrow, and then we'll pick it back up on Wednesday. So that's why it says review right there. So it'll be a review of how this class ends, which is a really big, important concept that some people struggle with, although hopefully you're not that one. And I will pick count it, one person to be my pointer. So what happens is when I point to you, everybody's going to get one throughout the year. And when I point to you, you have to say this one thing, and that's your only job for the rest of the year. But you probably want a better one than today. Right? There's some good ones, right? You can be today more, but you can't. But if I point to you, you have to say this each and every time. And what'll happen is we'll get a problem, and I'll say, "What do you think we do, class?" And the class will go, "I don't know." And then I'll point to Morgan, and she'll say her special thing, and then everybody will go, "Oh, I see it now." And it won't be chicken butt. Trust me on that. All right. Homework tonight. Copy down.
You have a stapler?
It's over there by the copy or printer.
Printer in here?
I do.
This is actually evens, not
Yeah. This is 2, 4, 6, 8, 10. Was this a class I asked? Is 0 even or odd? 0 even or odd?
I like it.
Or neither?
No. Neither.
What's the definition of even?
It's
Divisible by 2. Is 0 divisible by 2?
No.
So you can't do 0 divided by 2?
No.
So is 0 divisible by 2?
Yeah.
So 0 is an even number. You want to hear the formal definition? It has nothing to do with today's class. The formal definition of an even number.
Sure.
A number is even if it can be written as 2n, where n is a member of the integers. Right? What's an integer? 1, 2, 3, 4, 5, -1, -2, -3. So can you write 0 as 2n? Can 2n equal 0 if n is the value? Wait for an answer.
Yes.
Yeah.
Yes. If n is the value,
Yeah.
0 is, give me an obvious even number.
6.
6. Is 6 even? Well, it's even if you can write it as that. What would n be? 3. Right? Give me an odd number. 7. Is 7 even or odd? Well, if it's even, it can be written as, it can't be any number. I mean, you can solve this equation, but the solution for this is
3.5.
And 3.5 is not an integer. Right? Guess if that's the definition of an even number, what's the definition of an odd number?
One that cannot be divided by 2.
No, this is the formal math definition of an even number. What's the formal math definition of an odd number?
1.
We already determined that 0 was even.
1.
If you can write it as 2n plus 1, it's odd. So all odd numbers can be written as 2n plus 1. 11. If n is an integer and n is 5, 2 times 5 is 10 plus 1 is 11. That's why 11. All right. Just throwing that out. You won't see that until pre-calculus. Pre-calculus. All right. Everybody got the homework written down? All right. Here we go. All right. This is the 2-part day on segments, rays, and distance. We've already had segments. We haven't had rays, but you probably know what a ray is. I'm going to claim you don't know what distance is, but you will by the end of the day or end of class. 3 main objectives. We'll talk about them. All right. Recall. Anybody? The movie?
No.
Guess what it's called?
Total recall.
Total recall.
Total recall.
Okay. And that is the
Recall.
not that guy, but that is
Timmy.
that's the governor of California. Former governor of California. Arnold Schwarzenegger.
Oh, I've heard of that guy.
He's an actor. He was also a bodybuilder. He was Mr. Universe for, I don't know, umpteen
Oh,
years,
that kind of thing.
right?
Certainly.
And he later became, he's Austrian, who later became a naturalized citizen. So he would have been president. We would have elected him, in my opinion. We probably would have elected him president, but you can't be a president if you're born. All right, enough of that. Recall we talked about points. Points are not a size. They're not they're not a circle, although we draw them as circles. They're simply a location, space, and they're represented by a capital letter. We talked about space as the collection of all possible points. And we talked about segments or line segments. You can use either one. And we talked about how you name line segments. Line segments must always be named by, somebody finish the sentence. Any points?
The end point.
The end points. They have to be named by their end points. And for this particular one, it doesn't matter whether you go left, right, or right, left, but it has to be the end points. We gave this one example and we said, how many unique segments are here?
3.
We said 3. You have a small one, you have a medium one, and you got the whole darn thing, yes?
Yeah.
Okay. So the small one is XY or YX, the medium one is YZ or ZY, and the whole thing is XZ or ZX. Yes? Yes.
Yeah.
Quick review. Here's the thing that you got to lock in your brains. And I said, believe it or not, people are going to get this wrong when we have our first quiz. Segments have names, and then they have, well, what happened? How do you name it when you're talking about its distance or its size? For its name, you will always have the symbol, and for its distance, you will never have the symbol. Is anybody unclear on that? Okay. We talked about planes. Planes can be, some books will say 4 letters. Ours says 3 letters. 3 or 4 is fine. Any 3 points that are on the plane can be the name of the plane itself. I like 3 because 3 is the fewest number of points that you need. We did that little thing with Morgan's finger and your finger, and was it my finger or her finger?
Her finger.
Okay, it was you 3 fingers. All right, enough of the review. Let's get on to the new stuff. What if, start with 2 points, and this time, instead of stopping or going on forever in opposite directions, I instead, well, then that would make a line.
Stop at one and go on the other.
Stop at one and go on the other one. What do I make? What do I make?
Great.
I'm only going in one direction. So what do I make?
Right.
I make a bad boy band.
See,
Anybody? No, this is way, it worked well 10 years ago. It doesn't work now. You've never heard of the band One Direction.
Offer
Oh, that is, ladies and gentlemen,
Yeah.
that is the formal definition of array. Write that down. Book of Truth. Yes. The windows don't, they can open one time. No. All right, write this down, please. Write this down. Array and endpoints. Notice it doesn't say endpoints, singular endpoint. You start with an endpoint and you go in one direction forever, never stop. If you go in one direction and never stop, you're going to go through a point. In fact, you're going to go through an infinite number of points. Pick one, any one. Any point along the ray can be the name of the ray. I just chose Y. And let me say that one more time, make it really clear. Ray's name starts with the endpoint, and then you pick any point along the way for the second point. You need 2 points to name a ray. Colt, turn around. Make sure you have this written down. This is how we name rays. Make sure you pay attention. This is a critical point. Which way does this ray face? Goes to the right. Look at the symbol. What symbol did I use above X and Y? A right arrow. What would happen if this ray faced to the left? We would use a right arrow. Because what would happen if the ray pointed up? We wouldn't draw an arrow. So the symbol for a ray always points to the right, whether the ray goes to the right, left, up, down, or diagonal. Did you understand the point there? Right? It has to point to the right, and technically it's wrong if you point it to the left. The actual ray could point any direction. That doesn't matter. And then the second point there is the first letter of its name must start with
The end point.
the end point. It has to start with the end point. So it would be incorrect to call this
YX.
YX. That would be incorrect. That would be incorrect. It is not YX. In fact, there is no ray YX here. Yeah,
Supposed to know what direction it goes.
you don't. You don't. Did you hear a question? Well, then how do you know which direction it goes? And the answer is you don't, unless they give you the graph of the ray itself. What's the name of this red ray I just drew?
X, Y.
Very good. Which way does the ray face when you give its name?
Right.
Always to the right. Yeah? That's as hard as rays get until you get to pre-calculus. Physics class as well, too. We use rays in physics class. Except they're not called rays, they're called vectors.
That would be 2 years or
Yeah. Next year's chemistry. All right, we good? Rays? All right. Interesting fact, right? If you have a line and some points, how many points do I got here? Or how many name points? There's an infinite number of points since it's a line. There are 3 name points. How many rays are there? How many unique rays are there? How many? How many? How many unique rays do I have there?
Here.
He's going 4.
Four.
He's going 2. I heard a 3 as well.
4.
Pick a point, any point. Go in one direction. What ray do you have? You picked Y. Go in one direction. There's no other point, so I can't go in that direction. I got to go in this direction. So ray YX. Is that the same as YZ? Same or different? Is YX the same or different as YZ? That is the same ray. Different name, same direction. Because remember, it goes forever in this direction. So ray YX is going to continue. It's Colorado. It rains and hails all the time. We'll survive. All right. So that is one ray. Give me another ray that you see up there. Different ray. ZY. Is ZY the same or different as ZX?
Same.
That is the same. So I got 2 rays for sure. Anything else? XZ, different ray entirely. And then therefore you have, there's 4 rays up there. There are 4 unique rays. Anybody lost on that? Okay, I'm going to show you a couple of them. Right? Here's XY, here's ZY, here's XZ, and finally YZ. So those are all different rays. I'm going to circle 2 of them, and you need to tell me something smart. I'm going to circle 2 of them. I'm going to circle those 2. Tell me something smart about those 2 rays. They both don't go to the right. One goes left and one goes right. Tell me something about those 2 rays. She says if you put them together, you get the whole darn thing. True, but not the point I want to make. They both use the same point. So they both have the same end point. You see that? They both start at X and go in opposite directions. They do, in fact, make a line. If they start at the same point and go in opposite directions, we give them a special name. And that special name is opposite rays. Opposite rays share the same endpoint and go in opposite directions. In other words, they make a line. You need to write that down. Opposite rays, right? Opposite rays start at the same endpoint and go in opposite directions. In other words, they make the entire line. Those are called opposite rays. I don't have a red box up there. I probably should, because I definitely want you to write that down. Hey, this is the #1 question that's missed on the quiz. I'll say, name the opposite rays. You're like, I don't know what an opposite ray is. Opposite rays start the same point and go in opposite directions. To hammer this point one more time, right? Opposite rays. Are these opposite rays? They're going in opposite directions. So what would I have to do to make those opposite rays?
Start them both at C.
I would have to take my smart board and I have to press the button. They're not opposite rays. And I have to press the button and drag it over here. It's just animations. But thank you for that reaction. All right. Are they now opposite rays?
Yeah.
They are, in fact. So BA and BD are opposite rays. But remember, the symbol always points to the right, even if the ray goes left. or up or down.
Why?
It's just the way we decided to do things. Okay, those are the opposite rays. This is the number one missed on the quiz. I'll say name the opposite rays and people won't be able to do it. All right, in geometry, big picture, we talk about three things that are words you've never used in your life before until today. We're going to write these words down, and within a month, you'll be comfortable with them, but you won't be comfortable today. You're like, I know those three words, and I don't know what they mean without a book. I got to look it up. So you're just simply going to write these definitions down. We're going to use these words all the time. I'll reinforce it constantly. So here we go. All right. New concept. In geometry, we have rules, or we have laws of geometry. To become a rule or a law, it either has to be accepted as true, right, or it has to be proven. And we give special words or names to those things that we accept to be true or we've proven to be true. They're just words. You got to write them down. All right. Accepted without proof. We already talked about definitions. The triangle, because it's got three sides. That's a definition. We don't prove that. It's just a definition. The second thing, new word, we'll write down here in just a second, is something called a postulate. You've never used that word before in your life. These, both definitions and postulates, we accept them as being true without any proof. What must be proved, two versions of it. One is called a theorem. Maybe you've heard of theory, but you haven't heard of theorem. And the second one is corollary. Maybe you've heard corollary. That's probably the only one potentially you've heard of before. In geometry, definitions, postulates, theorems, and corollaries we use every day. Your entire book of truth is going to be full of these four things. Yeah.
Isn't like the Pythagorean theorem?
You heard, that's where you heard theorem from, right? Your teacher never explained it. Your teacher also never proved it to you. Guess what we do this year? I'm going to prove it to you. Like I'm not going to say, trust me, a squared plus b squared equals c squared. You will prove it that it's true. All right, now let's write these down. First one we said, well, we had definitions, but we're okay with definitions. Postulate. Postulate is a statement that we accept as true without proof. In the first geometry book ever written, it's over here, by an ancient Greek mathematician called Euclid. He's not one that came up with this. He just kind of put all the ideas together into one book, and he made a book that's called Euclid's Element. It is the second most printed book in the entire world. What's number one? Bible's number one. We get some more people that are Muslim to actually read and write. I guarantee you that book's going to take over. But for right now, as it stands, Bible's number one. This is number two. It is the second most published book in the world. The book you have in front of you is Euclid's Elements. It just got better pictures than boring stuff like this. They're colored, and the words aren't as strange because this one isn't written in Greek, but his sentence structure is probably not something we're that comfortable with. Once you finish geometry, you could read Euclid's Element and you would understand it, but you can't do it right now. All right. Euclid didn't call them postulates, he called them axioms. An axiom is Greek for it's worthy. Hey, you're worthy if you don't have to be proven to be true. You just are accepted as truth. Second new word, theorem. As Nikki said, Pythagorean theorem. You've heard of that before. This is a statement that we prove to be true. Theorem comes from the Greek as a proposition. Well, I'm going to propose that this is true. Well, you got to prove it to you. We never prove postulates, but we prove all theorems. Like I said, the majority of your book of truth is going to be full of theorems. I'll give you plenty of time to write this down, but I'm going to go on to the next one. The last one is the hardest one to remember what it actually means. There are some theorems that you prove to be true that are really easy to prove. And you prove them using other theorems. So when you have a new theorem that comes from an old theorem, hey, I take the Pythagorean theorem and I prove something else with the Pythagorean theorem. And it's really easy to prove. We don't call it a theorem. It's kind of like a mini theorem. We call it instead a corollary. And a corollary is a statement that's easily proven using a theorem. I never really understood when I first was in geometry in high school, right? The corollary took me a month or two to figure out what does that really mean. If you want to think of all these as postulates and theorems, you'll be okay. But when we get to a corollary, you're like, what the heck was a corollary? We're still going to prove it. It's like a mini theorem. But it's a theorem that comes from other theorems. Most theorems come from definitions and postulates, but some come from other theorems. We call those corollaries. And I'll leave that up there too. Everybody's got them all copied down. Cool? Anybody need more time? Okay. That was our first objective of the day. Is now you know what a postulate, theorem, and a corollary is. On to the second one. All right. What we're really doing today is we're going to be talking about distance. You've dealt with distance in your life before. We're going to give you a formal definition of distance and where it comes from, right? In other words, distance is measuring things. And specifically, since we really only have a finite distance, rays go on forever, lines go on forever, we can't measure them. The only thing we can measure are segments. This is going to be Morgan's baby, right? Not literal baby, but Morgan's baby, right? That when I point to her, she's going to talk to me about distance and segments. I'll tell you what you're going to say here in a little bit. All right. What do you need to measure distance?
2.
What do you need to measure distance?
2.
I like that. What would the average person say? What do you need to measure distance?
Ruler.
You need a ruler, right? Have you ever wondered where rulers come from? They come from
Greek mythology.
They come from the book that's in front of your face. The book that's in front of your face, which I'm going to call Euclid's Elements. That's the name of his geometry book. It's the book that you have in front of you. Stay with me, right? Tells you how to make a ruler. How do they make this ruler? Well, they use Euclid Elements. Let me explain it to you, right? You need a ruler. So what is a ruler? Ruler measures distance. I need a ruler. Let's make a ruler. Okay. We know what a line is, yes?
Yeah.
I'm going to take a line and put 1 point on it, yes?
Yeah.
Okay. Then I'm going to, as she kind of figured out, I'm going to put another point on the ruler, anywhere, or on the line. I'm going to put a point anywhere. Then I'm going to take my compass. Now I need a smart person to say something smart. What am I going to do?
Take the cap off.
Okay.
Connect the dots.
I'm not going to connect the dots.
Not connect.
Measure the
I'm going to measure the distance between A and B. There, I measured it. Now what do I do?
Look at the measurement.
No. What am I going to do with this measurement? That's how far it is from A to B. What am I going to do with it? Say again. Make another dot. And then do it again. And then do it again over here, and then over here. And I'm going to do that until I get tired. Guess what you just made? Just made a bunch of dots. It's not a ruler yet. So I'm going to make a bunch of dots, but all of those dots, using my compass, are equidistant. Well, what do I do now?
label.
What am I going to label them as? Ooh, instead of letters, how about we make one of those letters,
1.
or even, I would say rulers start with
6.
0. So I'm going to take one of those dots and make it 0. Well, then the next one's 1. And then if I make all the numbers evenly spaced, I have a number line. Well, how do you make a ruler out of a number line?
Take the pause.
Get rid of the negatives. I got a ruler. That's how rulers are literally made. No joke. That's how they're made. Right? All right. So now, because we want to seem smarter than everyone else, we're going to take that thing, which is that concept, take that, put numbers, make them equally spaced, and then write numbers and then erase half of them. We're going to put that in math words, what you're about to write down. Yeah. Yes. Good question. Right? It's called literally the rule of
Compass.
You've probably heard this story before.
Rule of thumb.
Somebody just decided that's an inch. And somebody decided that
That's a foot.
that's a foot. Rule of thumb, as the story goes, some king said, but let's make this worth an inch. Right? I don't have time now, but if you want to talk where the meter came from, that's a much more scientific explanation. I don't have time to explain that one, but I will at some point this year. All right, the first actual postulate in your book of truth, write this down word for word. It's called, because it describes how you make a ruler. And since we measure things in geometry, we need a ruler. Postulate 1, called the ruler postulate. You can either say because of postulate 1, or you can say the ruler postulate. The points on a line can be paired with numbers, real numbers. in such a way that any 2 points can be 0 and 1. It doesn't say specifically the middle 2 points. It just says any 2 points can be 0 and 1. But once you set up what's 0, what's 1, as she just stated, how do we figure out what's 1 dot? You've just now figured that out.
What's a fake number?
Who was your math teacher last year?
John.
Real numbers, as of right now, I would guess that none of you can think of an unreal number. When you take next year's course, Algebra 2, you get unreal numbers, except they're not called unreal numbers. They're called, no, negative 2.4 is a real number. But we have a group of numbers that are quote, quote, imaginary. We refer to them as complex numbers, really, but imaginary numbers. And we'll talk about in Algebra 2. If we have time in this class, I can talk about them as well too, but not today. We have real numbers and we have non-real numbers. All right, do you have this written down? Rule of postulate's going to come in 2 parts. This is part number 1.
What's the second part?
Well, I'll get to it.
Sure.
I'm positive. I'm not positive I will end the class with those questions, but I'm positive I will get to point number 2. All right, good, everybody? By the way, as Tess has her book open, she's going to notice that I'm just writing exactly what's in the book. So if you're ever copying down a theorem or a corollary, like, hey, you went too fast, it's in your book. All right, so that's the idea, or half the idea of number 1, or postulate number 1, first part. Now there's a second part. The first part says you can make a ruler, right? So rulers can be further divided. Instead of having 2 dots next to each other be 0 and 1, what would happen if I picked a dot way down here to be number 1? And I have a series of dots in between, right? Instead of picking these 2 dots as being 0 and 1, well, maybe I pick that to be 0 and that to be 1. Therefore, the middle dot is
0.5.
So rulers can be further divided. Get the picture?
What's the smallest unit of measurement?
I truly don't know, but we have lots and lots. You've probably heard of nano, right? Before, right? That goes on forever. It never stops. I just don't know where the words we have stop.
So say you have.
We have a billionth of a meter, a trillionth of a meter.
So say you have the lowest unit of measurement you can.
It can always be divided.
What if it can't be divided?
I'm going to run out of time and you're going to be responsible for all this, but I'm going down that path. All right, here's blow your mind number 1 of the day. Between any 2 real numbers, between 0 and 1, how many numbers are there?
Infinity.
There's an infinite number of numbers. Between any 2 numbers that you can think of, no matter how small, there's another infinity. This concept of infinity will cause you problems if you really start to think about it. Between any 2 numbers, there's an infinite number of numbers. No matter what 2 numbers you can think of, there's another infinity sitting right there. All right. Okay, I said 2 ideas. Here's the second idea. So idea number 1 of postulate number 1 is rulers can be made and further divided. Idea number 2 is that you measure distance using subtraction. We'll write it down here in a second. You measure with a ruler using subtraction. You're like, no, I don't. I just read numbers. Well, I'll show you what that means, right? Most people are like, you can't do that with subtraction. So let me show you. So how far is it between B and D? Well, we take our ruler, we push it up there, but I didn't put 0 next to B. I put 1 next to B because I'm doing it the hard way.
2.
Well, how is it figured out? You look at the coordinates of the point. What's the coordinate of point B?
1.
What's the coordinate of point D?
3.
Subtract.
2.
3 minus 1 is
2.
2. So it's 2 units, 2 inches, 2 centimeters, whatever your units are. But what if I went from B to D? Now what am I doing? Do the math. What's B? What's D? So that would be 1 minus 3, which is not 2, it's... So we have 1 extra thing we add to it. Guess how you figure out distance?
Oh, well, I was gonna ask a question.
Guess how you figure out distance? You take the coordinates of the 2 points, subtract them, and then these got to be the same number. They're not. How are we making the same number?
Absolute value.
Absolute value. That's how it's done. Distance is always a positive number. Distance is never negative. You can go in the opposite direction, but you don't go -6 miles. You go 6 miles in the opposite direction. Yes.
Is the ruler exact?
Well, the more accurate your tools are when you write. So the thickness of your pen, when you make those marks, a thick pen, that mark's very long. But where is the tick mark actually? In the middle? At the start, the finish? That's kind of a good question. So the more finer you make the tick marks, the more accurate your measurement is.
Middle.
Talk to your science teacher about accuracy of measurement. They can go on long statements about how that's done. I will tell you, if it's a decimal number, I will tell you what needs to be rounded to. Rarely do we need to round in this class until we get to trigonometry. Okay, do you get the basic concept of distance? Tonight for homework, they're going to give you points, right? Underneath the points are going to be numbers. They're going to say, what's the distance between this and this? They don't want you to actually count points. They want you to do subtraction. Take the two coordinates, subtract them, take the absolute value. Make sense? Okay. So this is your second statement. I said we'd make it complicated. Once a coordinate system has been chosen, this was her statement. How do we choose it? Just choose 2 points. We say that's a centimeter, that's an inch. The distance between any 2 points equals the absolute value of the difference, fancy word for subtraction, of their coordinates. Once again, if I flip the slide, you can open up your book to it's on the page, and I literally took it word for word. Okay, good. All right. Pretty cool. And it turns out that this is what allows you to add, subtract, multiply, and divide. Right? Remember, multiplication is just repeated addition. Right? We just said you can subtract, so therefore you can add. Exponents is repeated multiplication, which is repeated addition, so on and so on. Square roots, I'm going to have to explain that to you in chapter 11 or 12. All right, sometimes in geometry, things are weird and hard, and sometimes they are stupid, simple, and obvious. I'm about to give you something that's simple and obvious right now, right? I call it a duh. Remember, right? We can't do anything in geometry unless we prove it or we accept it to be true, right? So here's a duh. Ready? Think about this. If I have a segment, yes, segment's not a line, it's not an array, and I put a point somewhere in between the two endpoints, right? I have a long segment, the whole darn thing, AC. Everybody with me? This is going to be Morgan's baby. I have a medium segment, right? And I have a short segment. Yeah? Agree? All right. Tell me, what is the relationship between the long, the medium, and the short? What's the relationship between the long, the medium, and the short?
ABC.
The 3 points are collinear, but I said the segments.
ABC.
What do you mean ABC?
ABC.
Okay, that's not a relationship. What's the relationship between the segments?
ACBC.
This is why we need Morgan to have a famous statement. Guess what her statement's going to be? Once I say it to you, you're like, well, that was duh.
There's no.
Oh, no, there is a relationship. You ready for it? Right? The relationship between all 3 of these segments is I got a short piece, I got a medium piece, and instead of saying the long piece, I'm going to say I have the starts with a W. I got the whole thing. Now, can you come up with it? What's the relationship between the 3 parts?
Oh, they all equal?
You're closer.
They're all the same.
How about if I took the short piece and added it to the medium piece? Guess what Morgan's statement's going to be? From now on, if I point to you, Morgan, you're not going to say something silly. You're going to say short piece
Short piece.
plus medium piece equals.
Long piece.
So here we go. Let's try it out.
Short piece plus medium piece equals long.
That's going to be what I do. And when you guys are clueless like you just were, and I point to her, you're all going to say, oh, now I know what to do. Okay? So medium plus short equals long, or short plus medium equals long, right? This is actually the first big thing in this book, right? And this is postulate number 2. Postulate number 2 is called the segment addition postulate, the Morgan postulate, right? Because
Short plus medium was long.
short plus medium equals the whole thing, right? We say the long piece, right? Let's say the whole piece. Okay, so here it is. If I take the short piece AB and add it to BC, I get the whole darn thing AC. So if B is between A and C, then AB, segment AB plus segment BC has got to equal the whole darn thing. Short plus medium equals the whole darn thing. That is all of postulate number 2. And once you see it, you all should have the reaction of, well, yeah, of course, duh. But believe it or not, this one thing we spent a lot of time on, which is a good thing because it's an easy concept. Anybody feeling lost on that? Lost? Some postulates terms, you got a lot of writing, some it's pretty darn quick. If you need to draw the picture, draw the picture. If you're like, duh, I got it, make sure you still write it down. Postulate 2, segment addition postulate. If B is between A and C, then AB plus BC is equal to AC. Got it? What? There is. Okay. So how do I use this? Well, here we go. This is what your homework looks like. Those who are doing your homework, right? They're going to give you a segment. The segment's going to have an endpoints, and it's going to have a point somewhere in between the two endpoints. And then they're going to give you some information. You should take this information and do what? I should take this information and do what? Put it on the diagram, not in the book, on your piece of paper. How long is the short piece? So I should put 4 on the short piece. How long is the medium piece? So I should put 10 on the medium piece. And then if there's a question mark, duh, that's the question. So what is it asking us? The short, the medium, or the whole darn thing? So how long is the whole darn thing?
14.
Sometimes geometry is strange and weird and challenging, and sometimes it's simple and obvious. This is an example of until they make it more challenging. So how are they going to make it more challenging?
With less numbers.
Too many
More.
numbers. Lots of numbers.
He said less numbers, and I said more variables. So now they're going to throw some variables in there, right? Yeah, that one's really easy when there's nothing but numbers. Sometimes it's weird and hard. Sometimes it's simple and obvious. Now they're going to make it slightly more challenging. Instead of giving you numbers, they're going to give you expressions with variables. Here we go. Is it the same or different problem? Same problem, just with variables. How big is the short piece? How big is the medium piece?
X plus 6.
And
Short plus medium equals whole.
the short piece plus the medium piece is going to equal the whole piece. So go ahead, Brandon. Write the expression. Exactly what Morgan just said. Oh no, she said that everybody said was how big? Previous question, I said, well, how big is the short piece? You didn't say AB, you said
X.
You said X. So what's the expression?
X plus X.
Equals, and how big is the whole? 24, right? If you didn't catch that, the whole piece is 24. How do I know that? Oh, it says so. And then Morgan said short plus medium equals the whole darn thing. And so he finally said, well, the short piece is X. The medium piece is X plus 6. And the longest thing is 24. So X plus 6 is equal to 24. And guess what you're going to do now?
Divide.
Over the weekend's homework, which was
Algebra.
solving equations. And guess what you got?
An equation.
Equations that you need to solve. Group-like terms on the left side. What do you get? Group-like terms. What do you get? 2x. Next step.
Minus 6.
Next step.
Divide 2.
So do you have the answer?
X equals 9.
Do you have the answer? No, you don't have the answer. You simply have,
Part of it.
you just have what x is. Now you got to find the actual question. Where's the question?
Well, both of them equal.
It says right here, question marks. It says AB. So you go back to diagram, you find AB. AB is
9,
X, so therefore AB is.
9,
And it says find BC, and BC is X plus 6, so therefore BC is.
15.
All right, you got to be honest, and you got to be willing to sacrifice your self-worth and dignity in front of the entire class. I'm completely, totally lost, or yeah, I got this, let's go. But what'll typically happen is the whole class was like, yeah, let's go, and then you'll be sitting there like, I'm completely lost, and you'll be embarrassed, and then we'll be moving on when we could have had me say one statement and get you back on track. Lost? Good? Okay. All right, good job. Well done. Well done. That is a typical geometry problem this year. It's going to be a variable expression that you turn into equation, you solve it, and then you take the answer, which really isn't the answer, and you apply it to some other portion of it to get the true answer. Did you follow along what I just meant right there?
Yeah.
Right? You'll get to X, people put X equals 9, circle like, ooh, I'm done. You didn't do anything. You didn't answer any of the questions. Yeah.
So you're trying to find AB.
I am finding the question marks, and I'm going to answer that. That's going to lead me to look at the picture, which further leads me down another path that I may or may not be complicated or may be obvious.
Why is the X plus 6? Why is that?
Because that's how long it is.
Then why would it be just on one side plus 6?
I'm not following your question.
Why is the AB side only X?
Because they said so.
Okay.
It's that long.
If this was a word problem, they would say you have a segment broken up into 2 parts. The second part is 6 units longer than the first part, and the whole darn thing is 24. How long is the short piece? How long is the medium piece? That's how it would be written as a word problem. In a diagram form, I don't know. I mean, I think it becomes a little bit easier in diagram form than it does in word, but they'll give you both. All right. We have one more thing left, and it's pretty straightforward as well. All right, so the next idea is pretty big, right? So here it is. You ready? What do we got? How many? Are they the same triangle?
Yes.
If they were the same triangle, then everything about them would be the same. Do you agree? Well, what's your definition of same then? Oh, they're the same shape. I agree. They are the same size, different colors. So are they the same triangle?
No.
But do they have the same shape and the same size?
Yeah.
Morgan has stumbled upon the big concept. And the big concept is we give that a name. We give a name to same size, same shape, not the same thing. 2 completely different triangles, right? Hang with me, Morgan. This concept is called congruency, not equality. Equality means literally the same thing, the same values, right? Morgan, chill. Okay. Write this down, everybody, including Morgan. If you have the same shape and the same size, you are congruent. I didn't say you're equal. I said you're congruent. So we can't use an equal sign. We're going to use that symbol that you've probably seen before. You never knew what it meant. What's that symbol?
Equals.
Equal wavy.
Equal wavy. That is called congruency. Wavy is approximately. Okay. So if it's an equal sign with a tilde over the top, that means the shape is the same and the size is the same, but it doesn't mean it's literally the same thing. We got a red one, I got a blue one. They're not the same. They have lots of similarity. So much similarity that we can call them congruent rather than similar. We'll get to similar, but just not this chapter. Okay? There is a consequence for being congruent. The consequence is the size or the shape has the same size. So we can use an equal sign if we're talking about measurements. But if we're talking about shape to shape, we simply use congruency. Okay? Same shape? Are they both segments? Same size?
Yeah.
So are they congruent?
Yeah.
So therefore we can write the statement
AB is wavy equal
congruent.
XY.
AB is congruent to XY. The consequence of being congruent is that their values are the same. Well, segments only have one value, and that's their distance. So therefore, 18 is equal to 18. Yeah.
Alright, that makes sense.
Say that one more time.
I said that makes sense.
Okay, cool. The consequence of being congruent is that their sizes are equal. Notice for segments, when I talk about sizes, I get rid of the segment symbol over the top of it. Congruency applies to things. Equality applies to measurements or values. It's just the way we do things. I agree this is one of the silly things. I mean, they had to have it two ways because these two symbols are not interchangeable. You can't, if they're equal and you want to say they're congruent, you got to use congruent. If they're congruent and you want to say they're equal, you got to use the equal symbol. Everybody tracking? Okay. Also this, here we go. In geometry, if you are congruent, which means your measurements are equal, we can indicate that with tiny red symbols. I don't know why they chose red. They chose red, and it'll always be red. Sometimes it'll be black. Okay, so here we go. I have 4 segments there, yes? If I put their distances on there, or I told you that they were congruent, which ones am I telling you are congruent?
Why?
Top left to top right. If that's true, that means their measurements are the same, which means I can indicate that. And you indicate them with tick marks. A tick mark is, well, it looks like this. Do you see the little red thing right there? That means their measurements are equal. That means they are congruent. Well, what if I said the bottom? That means their values are the same. What if I said the bottom ones are congruent? Could I use tick marks?
Yeah.
But if I put one tick mark on this one, guess what I'm saying?
That's congruent to the other one.
I'm saying that this one is congruent to these two, so I can't use one tick mark, but what could I do?
2 tick marks.
That's what you do. This will get crazy when we deal with quadrilaterals because you might have 4 tick marks floating around. You
5
got 5, then it's just two. I've never seen more than 3 or 4.
tick marks.
All right. Did everybody get it?
Thank you.
You see tick marks, not only does it mean congruent, it means the measurements are equal. Okay? All right. Here we go. I got a segment, and I'm going to pick a point that's directly in the middle. B is directly in the middle. Well, what's the consequence of that? I put it directly in the middle. What's the consequence?
They're congruent.
What's congruent?
That A, B, and B, C.
Therefore, you make 2 congruent parts, right? If AB is equal to 5, well, then BC must be equal to 5. If I state that B is in the middle, right? You said AB is equal to BC. That is correct. We have a concept for that. And that concept of when you have 2 congruent parts, or you have something that's directly in the middle of some shape, we're going to call that, write this down, a segment midpoint. A segment midpoint. As the name implies, it's in the middle. And then we have one thing left, and then the bell's going to ring. No, I'm not sure, but I believe so.
I trust you.
There's nothing challenging about segment midpoint, but the consequence of a segment midpoint is that it makes 2 congruent segments of equal length. That's what congruency means, equal length. Same shape, same size, just different parts. Left side is not literally the right side. The left side is the left side, the right side is the right side. So I have 2 things that have the same measurement. They're congruent. Their measurements are equal. Hey, if I have a point in the middle, I can draw a line through it. I can draw a segment through it. I can draw a ray through it. I can even make a plane that goes through it. If that's the case, the thing that goes through the middle of point B gets a name. And we're going to call it a bisector. I'm going to skip to the definition. Right there. So if you have something that goes through the midpoint of a segment, that something, line, ray, segment, or plane, is called a segment bisector. I stopped right there on the plane because the plane is the harder one to visualize. But the definition does say a segment, a line, array, or plane that intersects a segment at its midpoint. That's called a segment bisector. You're cutting a hot dog in half. The knife is the segment bisector. The hot dog is the segment. I'm not sure why I was thinking of hot dogs, but I was thinking of hot dog. I'm hungry. All right. You have just enough information to do your homework because that's where the lesson ended. You didn't copy down your homework? There it is. And I will see you guys tomorrow.
You think there'll be practice still this evening?
I'm still looking. You can see the blue skies popping out right now. It was showing rain for this, but it was showing it's showing sunshine by 7.
Would this do Friday or?
It's showing sunshine at 4.
It looks like the storm's just.
Give me the very back. Yeah.
It's gonna be wet again.
You can just drop it in the box. Just drop it in the box.